Students, this is a great equilibrium question. It asks us to keep a lot of things in mind. First of all, they give us a nicely balanced equation. They give us information about one of the species at initially. They say there's 392 torr of ASH3 and it's placed in an empty flask. And then they tell us the total pressure at equilibrium. They say after 48 hours, which that number of hours is arbitrary. It just says after some time, the pressure in the flask was observed to be constant. That means there's no further reaction occurring, and that pressure at that point is 488 torr. So let's start by writing an expression for Kp, since they're going to be asking about Kp. With Kp, gases are of relevance, but solids are not. Solids do not belong in equilibrium expressions. So we have the pressure of hydrogen cubed and the pressure of ASH3 squared. That's how we'll end up calculating Kp. Now let's write an ice table out. The solid AS is part of the equation, but only gases and, as we'll see in the next few chapters, aqueous species belong in the ice table. So what I'm going to do is take that column under AS and just X it out because it has no bearing on what we do or consider. Let's start by listing the initial pressure that they had told us, 392 torr for ASH3, and it was placed in an empty container, so the initial pressure of H2 was 0. Now, without having to actually calculate Q and make the comparison to K, we can always assume that if there's a 0 in the initial line of an ice table, the shift will be toward the side with the 0. In this case, that's toward the side with the hydrogen. So I'm going to put a plus in the change line of the ice table under hydrogen, and a minus on the other side, the side with ASH3. We should also be aware of the coefficients. For hydrogen, it's 3. And for ASH3, it's a 2. So we'll be adding 3 times x for the hydrogen and subtracting 2 times x for the ASH3. And if we just add together the initial and change lines of the ice table, we arrive at 3x for hydrogen and 392 minus 2x for the ASH3. Now, for a little bit of Dalton's law, we know that at equilibrium, the total pressure was observed and measured. The two gases in the flask are ASH3 and hydrogen. So according to Dalton's law, the partial pressure of both of those gases should be equal to the total pressure. Well, they gave us the total pressure. They said it was 488 torr. That should be equal to the sum of the equilibrium expressions involving the other two gases. So the pressure of ASH3 we can write as an expression that involves x, 392 minus 2x. And then we add 3x because that's the pressure due to hydrogen. That all simplifies. 392 minus 2x and then plus 3x is going to work out to be 392 plus 1x. And then if we subtract 392 from both sides, we get a value of 96 torr for x. Now, we know that X has a value of 96, and that the equilibrium pressure of hydrogen would be 3 times that. So the equilibrium pressure of hydrogen works out to be 288 torr, which we're going to end up converting into atmospheres before we plug into the expression for Kp. So, and furthermore, WebAssign asks for the pressure in atmospheres. And that works out to be 0.379 atmospheres. For the other substance, the ASH3, 392 minus, if we know that X is 96, and we crunch those numbers, that works out to be 200 torr, and we'll also convert that pressure into atmospheres. And that one works out to be 0.263. So now we have 2 equilibrium pressures for each of the 2 gases, and they're simply going to ask us to calculate Kp. Oh, so we can actually, we've already answered part A of the question. They wanted the equilibrium pressure of hydrogen in atmospheres, and it's 0.379. And now to finish off the problem, we're going to finish our calculation of Kp with numbers to plug in. Once again, the pressure of ASH3 in atmospheres is 0.263. And after crunching those numbers, we come up with a value of 0.787.